Okay.
Let's begin. So, I wanted to wrap up with pretty much one thing I want to talk about, which I'm not going to go into too much detail or even really require you to even do a problem like this on the test, but I think it was worth mentioning. So that you're just aware of the idea. How do we know we can use power series to actually represent functions? And this question, the answer actually comes from Taylor's inequality. So the guy who came up with the Taylor series, he didn't just say, "Oh, this looks cool and it seems fine," but he actually went further and proved how much you could rely on this and what it actually means. So let's just talk about that for a little bit. So let f be a function. And what's the form for its Taylor series? Centered at x naught.
F to the nth power times x.
It's not f to the nth power.
Oh, I mean nth derivative over what's it called, n and the or oh, sorry, and times x minus x naught to the nth power.
You guys need to know that by heart. It's very important. Okay, so that's called its Taylor series. And so now, to see how good this is, basically we consider the difference between f and the Taylor series. So let's look at f of x and subtract, let's say, the kth partial sum, and it goes from k, of its Taylor series. Nth partial sum of its Taylor series. And we're going to look at how far apart are these two things actually, especially as n is approaching infinity. Okay, so as we keep putting in more and more terms, I want to call this guy something. Customarily, we'll just call it big T sub n. Okay, now we can define the difference f minus big T as, say, r sub n of x. This is called the remainder term. So that's what's left over after you take the actual function values and subtract the values that you're outputting from the Taylor series. This is called the remainder term. And so here is basically the idea. Here's a theorem that says if the remainder term approaches 0 as n approaches infinity, meaning you start to add more and more terms of the function, if the difference between the function and the Taylor series, because after all a function is just represented by the output values corresponding to some input values. So the values outputted by your function and the values outputted by the Taylor series are actually, that difference between them is going to 0. Pretty much that means they're kind of the same guys. If the difference between those two guys are 0, it means that they're the same. As n goes off to infinity, then f can be represented by its Taylor series, i.e. f is indistinguishable, mathematically at least. Mathematically indistinguishable. Meaning, yeah, like me writing down a function and me writing down the Taylor series of a function, there is no difference mathematically, as long as this is fulfilled. So if the outputs of my function are pretty much the same as the outputs of the Taylor series, then why is there a difference between the function and the Taylor series? There should be none. So you can actually prove that. And so we may, on any interval where the Taylor series converges absolutely in the above case. So, assuming this is true, and we are on an interval where the Taylor series actually converges absolutely, meaning that if I rearrange the sum, it's not going to change, so I don't have to worry about if I take a derivative, doesn't matter what order I've taken different derivatives in, or integrals, or etc. Then on any interval where the Taylor series converges absolutely, and it fulfills this property, we may replace f by its Taylor series. And if f is a function that can be represented by a Taylor series, then f is called analytic. So the analytic functions are super nice functions, they're super important, and we're not really going to talk about them other than I'll ask you to find a power series for some of them from time to time, but especially if you go off into complex analysis or something like that, knowing a function is analytic can give you a lot of power. So we can talk about the analytic functions, the functions that can be represented by a power series. And now the question is, how do we actually know that such a thing would happen? Or when such a thing happens, how would we know when it happens? How do we know this happens? Well, that is where Taylor's inequality comes in. So there's a theorem. The theorem is called Taylor's inequality. The inequality, this theorem says the following, using the same notation from before. Suppose the expression for the n plus first derivative of n is less than or equal to b on an interval, say x naught minus x, x naught minus r, x naught minus r, comma x naught plus r, where b is a constant. For best results, minimally chosen. Okay, so you don't just pick any random number bigger than the derivative. You want to actually squeeze it as small as possible. Otherwise, you might have to compute more terms to get it to work than you'd like to. So suppose our n plus first derivative, it's in magnitude is smaller than some number that I can pick. So say, okay, if I compute this, whatever that expression is, it's always going to be less than 5 on this interval, right? And I can pick a number 5 and make that true. Then the remainder term will be in magnitude less than or equal to b over n plus 1 factorial times x minus x naught to the n plus 1 for all x in the interval above. So you can always approximate the remainder by this other function, and as long as that function behaves very nicely, and so Rn will approach 0 if this guy approaches 0. Technically you can put absolute values, but you don't need it. X minus x naught to the n plus 1. Approaches 0. And so if you're looking at a particular function and you're concerned whether or not it can be represented by its power series, what you would do is you would set up this expression, and there's some interval that you're going to care about. What you're going to have to do is look at the expression for the n plus first derivative of the function you're considering, which we know we can find because Taylor's the only way it would have a Taylor series in the first place is if you can keep differentiating infinitely often. So you would be able to find an expression for this. If somehow you can bound that by a constant on the interval, then this guy, we can use this to talk about the remainder term and determine whether it will converge or not. And that's how we can tell. So we may determine with Taylor's inequality it's one of the most popular ways, whether f, the phrase to use is f converges to its power series. The power series converges to f. Or you can just even use the new phrase, whether f is analytic. Meaning the power series converges to f, and it converges in such a way that with enough terms, they're indistinguishable. I can't tell the difference between the two, which means if me plugging something into f is the same as me plugging something into the power series, and me differentiating f is the same as me differentiating the power series. Me integrating f is the same as me integrating the power series. It's not going to actually make a difference at the end of the day. So yeah, that's kind of nice. So to construct the Taylor series wasn't actually that complicated. It's nice that something, relatively speaking, so simple, which is also so powerful, actually does work out, and we can tell when it works out by something also not so, well, to actually derive its improvement, it's kind of complicated, but yeah, it's an easy check to know whether or not your f is analytic. Now, of course, in this class, every time I ask you about, oh, find the power series for this function, and then approximate this integral, it will be the case that f will be analytic, so you won't have to check, but I just think it's something that it's good to know in Calc 2, so I wanted to tell you guys about that. Something that's pretty cool, and if you're going to go anywhere in math worth going, an idea like this is going to be very important, very indispensable. Because sometimes functions can be difficult to deal with, but power series are very nice to deal with. Yeah, so that's that. That's kind of all I wanted to say, pretty much. There are some other techniques that you can use power series with like to find limits and things like that, but I don't know. I probably won't even ask you about that. We already know enough about limits already. So yeah, I think that's it. We're done. You guys feel happy? So, let's see. So we have a few minutes. In the remainder of the time, we could do some more examples, but I think instead what I would do, since we're very close to the final, is have you guys do some examples. So we're going to do the whole worksheet thing again, and I will post the answers online for you to check, and that's it, unless there are any other questions. Any questions about anything? You guys know when our final is, right?
16th.
It's the 16th. Huh?
Is it in this room?
The final exam schedule is, at this point, it's fully populated, so it will tell you literally everything, including where it is. Let's see.
I'm looking at James.
Yeah, so December 16th at 5:30, and it's in this room. Yeah, yeah, like during regular class.
Yeah. When we always